So this is the first lecture that kind of outlines our research program. This is the program that's still ongoing, that's been ongoing for maybe like 10 years or more. It's a research program to see if these concepts of dynamical field theory might ultimately lead to higher cognition. So here I only mention coupling among high dimensional fields, and that's the entry into that. So the goal is toward higher cognition, and we'll be working with that pretty much the rest of the semester. So it's ongoing research in a sense. We're giving symposia on that, talks on that, we publish on that. This is all ongoing work. This is sort of our current challenge and something we do in our summer school and so on. So it's fun, exciting, and we can also actually discuss interesting contrasts to other approaches toward that same goal. You know, some people might think that neural networks in the manner of, for instance, deep neural networks or transformer networks would maybe also be a route toward higher cognition. That could be, you know, how nervous systems do higher cognition, and then I could have to say something critical about that. So, but we'll first start with DFT itself and develop the concepts. And so we'll do this in, I think, 4 or 5 steps. So this lecture and the next lecture, I lay the foundations for that. That's really these couplings among high-dimensional fields. You will see not awfully high-dimensional, but still more than just one-dimensional fields we did so far. And then, so this will be 2 lectures. I don't know exactly how far I'll get today. I've planned a pretty short lecture, but if there are little questions, I can actually already start a little bit with the next one. And then in January, we'll talk about how sequences can be generated autonomously. And we'll talk about grounding of language and nested phrases and more advanced topics like that. And then finally, I'll talk about intentional agents and artificial minds in a way that have goals and acquire knowledge and achieve things in the world. Okay, so let's jump right into it. And so overall, the research program I outlined earlier was that DFT does, you know, the claim of this embodied cognition neurodynamics approach is that everything in the mind is done in sensory motor style, right? That was what we claimed. And that meant that concepts that are necessary because of the sensory motor nature of motor behavior, for instance, are the language in which we also look at higher cognition. So the first 2 points were things that we discussed in the first part of the lecture, so that the fields represent continuous spaces. We call those feature spaces, and the activation is a continuous state variable for these spaces, and that then neurodynamics leads to instantiations of units of representation, these peaks, and the instabilities make it possible to be flexible about those, create them, keep them work memory, make selection decisions, and so on. And so now today I'm going to show how coupling such fields leads to elements of higher cognition, particularly binding. I'll be talking about binding. And then, you know, as I mentioned, we will cover autonomous sequence generation in January. So here's the plan for the next 2 lectures. Today I'll do the first 2 points, and then next week I'll do the second 2 points. So first I'll talk a little bit about binding. I'm supposing that few of you really know what binding is. I wonder if we could make a quick vote. Maybe you could raise your hands if you, these online hands, if you know roughly what binding is or you've heard about binding. Do I see no hands, or am I seeing this incorrectly here? No hands raised, yeah? Is that right? No, I got a hand. Okay. At least one person knows what binding is. But I would assume that most of you don't really know much about it. Okay, good. Yeah, so it's useful that I actually introduce that a little bit, and then we'll talk about joint representations and within that then about, sorry, I need to get rid of here of this bar. I don't know why. I don't know if you also see this green bar. Oh no, I know how to get rid of it. Good. And then I'll talk about how we do binding in dynamic field theory. Good. So here an intuition for binding. Look at this picture here and just look around it for a while. And after you've looked at it, quite a number of items here, right? I'm going to ask you to pay attention here to this red cutter. Yeah. And so I can ask you, where's the red cutter, right? And you would probably be able to know it's somewhere here, for instance. Or I could ask you, what was at this location? And then you might be able to recall, to a separate experiment, recall that it was the red cutter that was at that location, right? So that would be an example of space feature binding. It's sort of a classical notion that different features here actually already used category like cutter, but you could also say it's a red thing. You might not even know what a cutter is. The sort of German would be Teppichmesser. It's a special kind of tool. Even without recognizing the truth, you see a shape, you see color, and you see features of it like orientation and so on. I have asked you about those, and all of those are bound. Here I demonstrate the binding to location. That is, you're able to say what is at a particular location, or you also just say where a particular set of features is located. But there could also be binding among these features. So, for instance, in a picture like that, you could say the blue thing is round, right? Or the screwdriver is green, or it's longish, or it's vertical, things like that. So this is a notion that has a lot of history in psychology, and it's a notion that feature values that pertain to objects are bound, and that for a very long time, and there's still actually ongoing research about that, uh, you know, could be the same as saying that everything is bound to a location because objects tend to be localized. There are some subtleties about that. Localized in which space? Is it a space that's tied to my perceptual system, or is it a space out there in the world? Are we flexible? Can we shift things around and so on? So there's some interesting current research on that. So that's classical notion of feature binding. So binding, as I already alluded to, can also be to categories. So for instance, here you could say, you could ask you what color is the S, right? And you find the S, and then you look up that it's green. I'll illustrate that example again. I think next week I will show you exactly how we do that neurally, which is it certainly hints at something that goes a little bit beyond what we discussed so far, because you would say the categories are not necessarily just feature spaces, right? The categories are maybe discrete different nodes, and how do you bind nodes to space, or do you bind nodes to other feature dimensions? Something to look at. So this notion of binding in psychology has a long history and plays quite an important role in higher cognition. And one reason why it's considered an important issue is that it is not a strict, just feed-forward feature extraction operation. It has more flexibility than that. And that means that you can potentially bind into objects feature combinations that you never saw in that form before. The classical example was to say a pink elephant, which I think now pink elephants have been used so often in cartoons and in movies that maybe it's no longer true. But maybe I could think up a new example. I don't know, some animal in a very unusual color, or some strange visual appearance of a category that we have some expectations about. And you can immediately describe an item like that. You can remember an item like that. You could say, oh, the elephant was pink, for instance, and so on. And so that's a form of flexibility that goes beyond having learned all the properties of a particular category. Like when you say, okay, I've learned what an elephant is, then there's a neural network in my mind that can activate all the features that are necessary for something to be an elephant, or actually conversely classify something as an elephant based on all those features. Then a pink elephant would be presumably something that you never saw before. So you couldn't have develop the neural connectivity to represent that pinkness of an elephant. Again, we might have to update that example because that's become a rather common appearance, even though I'm not sure I actually remember any pink elephant having really been depicted outside from psychology textbooks. Anyway, so one experimental demonstration of this form of flexibility is that sometimes there can be mistakes, misbindings, sometimes called illusory conjunctions, in which you're not attributing the features correctly to an object, and that reflects that you're flexible about attributing features to an object. So in one experiment that goes back to Anne Treisman, who's a very influential figure in this field, she died unfortunately a few years ago. She did this, she was actually quite old, she just died of old age. She did this series of experiments where she asked people to look at an array like this. I actually put the colors on top. The original publication is in black and white, and they use these funny patterns to illustrate the colors. So people look at this array, they have some time, just like I give you some time. And the reason why I gave you time is actually that you need to attend to the individual objects to do well on a task like that. And so you need time to attend either by gaze shifting or by covert attention, by just shifting your mental eye to the different items. And then after this time, the scene is removed from the visual array, and then you are asked to first report the numbers here, 1 and 8. And that's really just to make some delay, because these illusory conjunctions occur more likely if it's really from working memory. So if there's some time that has passed, it also depends on how many items you have here. You see here 4 items, 4 objects that will be taxing working memory, as we discussed, I think last week, or maybe, I think last week, the capacity of visual working memory is approximately 4. So this would be at the upper limit of that capacity. And then you're asked to report object features. So you're, let's say, asked to say there is a yellow circle, filled circle, or say green open circle, or a blue open triangle, or a red filled triangle, and so on. So the correct response would be listing all the features that apply to a particular object. And so what happens is that you have sometimes illusory conjunctions, that is, you report features that did occur in the array. So you have a higher rate of reporting features that are in the image than features that you just make up. You say a lila or a brown, or I don't know, a linear object. Now here you would report triangles and circles, and you would report the colors that are seen and open and closed. But you you swap features. So you would say maybe the large yellow triangle. No, it's not likely to happen with the small item. Actually, the small blue circle that's open. So you swap the feature of one of those objects to another. That's called an illusory conjunction. And so that shows that this form of binding is flexible. And that is a key to higher cognition. I'll come back to that. So Anne Treisman developed a theory that's still sometimes called FIT, feature integration theory. That's very influential. I mean, it's a verbal theory. This diagram here is from one of her papers, and that's sort of the style in which FIT theory was done. It's an interesting style in that this theory mixes neural metaphor and information processing metaphor. So at the bottom here, you see a spatial representation of the visual array with the stimulus projecting somehow onto this. And there's the notion of spatial attention. So what I just alluded to, that you would be looking at particular locations, particular objects in space, or you would also be attending to them covertly without shifting your eyes. That itself is a whole topic of how that actually is measured. It's only indirectly measured, but there's a very strong consensus that we do something like that. That is, there are only certain regions in space at which we are even able to report about such items, and that, for instance, that the amount of time needed to encode a scene depends on how many different locations there are, which is consistent with this idea that you have to sequentially look at every object or location. So this here at the bottom is the spatial attention. And then the notion is that the different features would be in different maps. And we would now say they would be neural maps. And in treatments is sort of implicit. That is, they are all spatial. They have retinotopic representations. And then they would represent different feature values. For instance, for orientation, you would have a whole layer of neurons that represents one orientation, another layer represents another orientation. So it would be sampling the different orientation, maybe similar for color. So this is similar to the color space fields that we'll just be looking at. So that is sort of neural, even though it doesn't explain exactly how this happens. It is the notion would be that if you have a location that you attend, then you enter at that location into your different feature map some activation that represents here the color, for instance, and the orientation, let's say. And then you would be extracting all the properties of the object from one particular attention selection and one particular location into a working memory of the bound objects. Now you consider these features to be bound, and now you would say, the red is the horizontal, and that's in your file. That's where they used information processing artists, that you write a file, and that file stores the feature combinations. So this latter part you can see is clearly not really neural. How do you create a file and store something and store feature combinations and so on? But the former part is. And so our task is to explain neurally the latter part, how the storage happens. And that's something we'll do. And so I will, according to plan, I would be coming to this only next week, unless we go really fast this week. Yes,
I
please.
was wondering whether how this feature integration theory would explain the Stroop task, for example.
You mean the Stroop
Yeah,
effects?
yes, that one.
Yeah, the Stroop effect. So in the Stroop effect, let me first report that to everyone here who might not know that. For instance, you have the task of reporting the color of a letter, just like in this example I showed here, or of a word, the letters of a word are written, let's say, in green, and the word reads red. It is the word for red. And when asked to report the color of the letters, people are strongly influenced by the meaning of the word. And so they will make errors where they report that the letters are written in red when the word says red, especially if they are asked to do this very fast. And also if you look at their reaction times, they will be much slower in reporting the correct letter color if it conflicts with what the word says than if it doesn't. And that's quite an astounding effect, because it is reading is a learned skill. It's not something that is wired in the brain at birth. And it's still so powerful that the meaning of the word overpowers this task of looking at the elements. And there are a lot of different variants of that. I would not really think that it's directly a probe of binding. It would usually be considered to be more a difficult, so a competition between different sources of specification. So here would be a source, the visual color you see, and then the word meaning, and they interfere at the level of generating the response. It is sort of taken for granted that you are attending to the word, and that will be the object here, the word, and that you are therefore localizing already, so you're not actually combining anything from another location, like a word written somewhere else, written in another color. So it's not directly a probe of binding, even though the task itself sort of makes use of that. I mean, this meaning of binding is really always probed in working memory. That is, you're not doing this task when you're seeing the letter. when you stored it. And there could be illusory conjunctions like that, maybe connected to descriptors when you do it from memory. I don't actually know. I'm sure there have been so many studies, probably somebody also studied what happens when you do a Stroop from working memory. Okay, thanks for the question. Good. So why is binding such an important issue? I'll just hint at that. So this classical feature binding that I referred to, that's what we'll first study. And that was, well, influential because it's really about working memory. And working memory is sort of as the word says, the tool, the basic tool for any kind of cognition, for thinking, for being in the here and now, for operating, for applying operators to something. You always have to have it activated. But you could, well, it's actually still a research topic after so many years. I mean, and Treisman died in the meantime, right? It's like 40, 50 years old, but it's still on. Just as economics, there were a lot of sessions about different subtleties about how working memory actually interacts with all the different processes. But the larger influence is that as you go to even higher cognition, especially language, concepts, relations, forming new concepts by combining other concepts, composition, as cognitive scientists call that, the notion of binding seems essential. And so here I'm just hinting at that. We'll come back to that in more sophisticated form in some lectures in January. So this is one variant from what is called vector symbolic architectures, going back to Smolensky. Some of you might have heard that name. So it's early attempts by connectionists to go to higher cognition from their neural networks. An attempt that has not become mainstream, and this vector symbolic architecture is perhaps the branch of this sort of thinking that is most alive, and I would say it is alive in research. It's not maybe alive in terms of a real neural account for cognition, but in terms of a neural network kind of artificial neural network kind of account. So just to illustrate the idea, so this is dealing with problems like combining symbols into phrases, for instance, that have meaning. For instance, here the problem is to express that, for instance, John loves Mary. That will be the sentence, right? So that means you have two objects, John and Mary, people in this case, and they have a relationship, one loving the other. That's a directional relationship. And supposedly that's very flexible. That is, you could express, I mean, John and Mary, of course, are generic names. You could maybe mention a name you never heard before, or refer to a person you never met before and you have no neural representation for, and then express a relationship like that about these two people. And how would you neurally do that? You certainly can't have a neuron that is tuned to that particular phrase, right? Because that would mean that every possible phrase has some neural substrate for it. And so this is a real challenge for neural networks. There's a constant struggle for how to do that. And so this idea, again, that goes back to Smolensky, was to say, well, I have some neural representation of these concepts, John and Mary, and for now doesn't actually discuss how that comes about, how I have that initial idea. And so here, for instance, in the tradition of distributed representations, this would be a vector of neurons, and in VSA it will be a large vector, high dimension vector with maybe 10,000 or 100,000 neurons. And the particular activation pattern of that vector would make it a vector symbol, neural representation of a particular concept, let's say the concept of John. And there are all kinds of questions to be raised about that from our point of view. I mean, how can you keep a complicated neural pattern like that activated? What is the working memory of that? We would say that requires some interaction where locally some of those nodes have to self-excite and they have to suppress others so they're off. And that's one source of criticism of this way of thinking. But deep networks, for instance, transformer networks also work with these high-dimensional activation vectors without actually saying how they could be stabilized. They don't have that notion. They just somehow set them by input. So it still supposes that you have such a vector for any
Can I
word.
ask you a question?
Yes, please.
So in this vector symbolic architecture, so this planning, this binding is taking place in someone third person's system, or this is just, for example, John's or the Mary's representation system?
I didn't quite, not sure I fully
So
understand.
this symbolic architecture will binding or will planning in third person's memory, or just this is from perspective of John's system or Mary's system? Will there be any difference between these binding systems?
So this is certainly an attempt to explain how an individual would represent such a concept in his or her mind, not an attempt to really deal with language in terms of communication, of how you would tell someone else about that, even though the assumption would be that when people communicate about such things, they have to create in the mind of the other person a representation of that nature. But that, of course, requires other processes like transforming a representation like that into ultimately speech, and then or writing, and then other person decoding that, and then there's the whole problem of grounding, namely of knowing what that vector John refers to. For instance, if you're standing in front of that person, to know who's John, or if you experienced John in some past, to know what person is being referred to, or even like from just a story you read, to know that that person showed up somewhere else. So all of these problems also need to be addressed. So this is just the very small portion in which you're trying to say, can I compose a representation of something new where John loves Mary? I don't know if I answered your question.
Yes, thank you.
Okay, good. When I manipulate, do you actually now see also the video images on top of the screen? Maybe you don't, right? You just see my slide, right? I actually don't know. Yeah, okay, good. So I'm always worried because this kind of covers or occludes something on the slide. So I'm not exactly sure how that shows up for you. Okay, so the notion that is of binding that is done in these kind of representations, these kind of approaches, is that you would have a joint representation. And that first I have to say actually something here about lover. So lover is one way of how you can represent a relation. So rather than directly represent that John loves Mary, you give John a role, that of lover, and Mary a role of being beloved. And then you actually also have to say that a lover and a beloved together form a love relationship. And I'm not going into the details of that here. And so the binding that takes place here is to tie that role of being the lover to John. And you would similarly tie the role of Mary being the beloved in a similar form. And then you still have to say that these two correspond to each other. So lover would also, this role would also be represented by a vector. And then the notion would really be that you would have a joint representation. So this square here is supposed to be somehow generated as a direct product of these two vectors, as a joint representation. That is, that whole vector now together means both lover and John is the case. And this VSA is all about reducing the dimension of this matrix to have the same dimensionality as the original vectors, so that you can treat this square here just like another vector, and that would be the vector of John as lover. And therefore now you would have a new concept in your mind, John as lover, that can also then be bound again to something else. And you can see how that would give you some form of recursiveness, that now you can build more and more complex concepts by just always binding them. And they have a proposal based on the fact that these vectors are high dimensional and random. That means in this matrix, there is a lot of redundancy when you do the direct product, and that redundancy can be compressed and can be compressed down to vectors of the same size with some error that they then look for how to correct and that's what they call binding. And we'll see that we do something not exactly like that, but something that plays a similar role. I think this just is the text that goes with that explanation. So this is a larger topic, and I'm just sort of hinting at that. And that's why this concept of binding is so prominent in attempts to explain higher cognition by neural networks. That's really what it is. And so we'll be addressing some of these forms of binding. In our terms, there are actually subtle differences, and these I try to work out in these 2 lectures between different forms of binding that are not always kept, or these differences are not necessary in other accounts, but in our accounts we actually see there are some differences, and that's what I'm trying to explain in the next couple of slides. But I just want to give that background so you know why we're even talking like that, why we're talking about binding. So again, the fundamental problem of representing something new you never had before with a neural network, right? Well, neural networks, as they are naively conceived in connectionism, have their connectivities all learned, and therefore they reflect what you've experienced in the past. And so it's not clear how you would represent something that is a unique new instance, right? And this capacity of neural networks to generalize is not about representing something new, but about actually invariance, that is being able to recognize a pink elephant as an elephant, right? But to recognize that it is pink as well. That is sort of the special feature we're talking about. Good. So how do we go about that in DFT? So first I'll start very simply. First we'll have to think about joint representations, and I'll explain here that joint representations, this is sort of the program here, enable I'll come back to this. That sort of announces where we're going. So let's first think about joint representations as anatomical binding. So we've kind of alluded to that before. We've alluded to neurons that are tuned to multiple parameters. For instance, we introduced earlier this notion that there could be motion detectors in the brain, and there are actually neurons in area MT that are like that, that represent both a property of motion, like the direction of motion, and the spatial location of the moving object. And so the neurons would be tuned, in other words, to space. They would have a retinotopic receptive field probably, and they would represent something like motion direction. First of all, they represent motion per se, so they only go on if something moves, not if there is some visual structure someplace. And they might really be tuned to move in direction that is only fire when motion goes in particular directions. And Hubel and Wiesel actually already have hints at that. It's not exactly, it's a combination of motion and direction that of movement direction and orientation, and it's actually in higher cortices that you extract the motion direction independent of such things as orientation. But it's already sort of the same kind of nature. And I've argued similarly in the motor domain that different parameters like movement direction, movement amplitude might be combined so that you have certain neurons that fire for particular combinations of these values. And that's how you could represent both of those things in the population. So I call this sometimes, here I think I have one more slide here. This is Hubel and Wiesel, right? Hubel and Wiesel have both the receptive field, that is this dashed line. That means that you are specialized to a particular location in visual space, and the orientation. So the neuron combined represents 3 things: the orientation and where the stimulus is in space. And that can be more. Sometimes it can be another 3rd and maybe 4th parameter that also influences the neural fire. And so that's not surprisingly, we've already looked at that. And now one could say, well, that is a joint representation of these different qualities of color. Here I take color as a feature value in many of the slides now, just because that's so convenient for us, even though literally that's not actually correct in the brain. The color is not represented as an axis, it's represented as sort of opponency pairs. There are 3 kinds of opponency pairs in color space, and they are arranged in some special forms called color blobs, where the 3 types of opponencies are represented by different population of neurons. But that's not like an implementation detail, let's say. And we conceptually just use hue, which is a periodic but continuous space. So the red ends here and starts here, so like on a circle. And that's one way of representing color psychophysically, and that can also be used in technology. And so we're using this metaphorically as a neural representation of color, even though the details are a bit different, just because color is so convenient to show. So here in a slide like this, there would be the notion that along this dimension, the color represented by those neurons is varied. The color meaning that red items are located here, and blue items here, and green items there, and so on. And here it's a bit confusing. This is the color here is a color code for how activated the field is. So blue is below threshold, and red is above threshold. This core here of red, right? So that these colors here of these peaks have nothing to do with this axis. We never even thought that it could have, but then some listeners sometimes really got stuck on that. So it's a bit unfortunate that we use the same color scheme for representing the actual hue value along this axis and then the activation levels by some color code. So it's a joint representation in the sense that any combination of a color value and a spatial location has a neuron or a whole group of neuron that's tuned to that. I call that sometimes also anatomical binding, because you have anatomically all the different combinations in the form of different neurons. So their connectivities are such that every combination is represented. So the notion would be that if you have this kind of visual scene on your retina, and I'm assuming this is just one-dimensional. It should have, here it's a bit two-dimensional, but we're just looking at the horizontal in order to make these plots simple. Of course, in reality, it will be a two-dimensional field, and this joint field will be three-dimensional then. So here along the horizontal would be spatial location, and along the vertical would be color. And so the notion that these neurons are tuned to both dimensions means that if you give this visual input to the scene, it would directly create these activation patterns where at this location of the green item here, you would have a peak that is localized along the color dimension at green, and along this location in visual space, you would have a peak of activation at the location along the vertical axis here that corresponds to blue. So this blue here corresponds to the location of that peak. And so these two peaks arise by virtue of the forward inputs that make the receptive fields, right? That would be a forward connectivity that in our models we would have to model by mapping a computer image that is input to the program that runs the field, such that it sorts the pixel by the hue values that it gets from the camera, and then arranges for some intensity variable inducing the peak. The intensity variable in color space is called saturation. So when you get a green that is very pale, very low contrast, there will be a low input. If it's a very bright, lot of intensity green that sticks out from the background, then that would be high intensity. That makes these inputs. And so in this representation, it's sort of trivial, if you wish, that we have a bound representation, because the neurons, it's all arranged to have all the combinations given. But later you'll see it's a bit more complicated when we get to more abstract spaces. Yeah, so these two peaks would represent this visual scene. So that's kind of that's called a joint representation of these two feature dimensions. Now, if you have a scene like that, you could unbind, right? In this representation, it's bound, but you could now unbind by extracting the individual information. And you could do that, for instance, by projecting into lower dimensional fields that are specialized for one of those subdimensions. Here, for instance, a field of activation only defined over hue, over color, and a field that's only defined over space, it's purely spatial receptive fields. And you would extract, the bound input into these unbound lower dimensional representations by projecting from this joint representation into these lower dimensional representations by what we call a contraction mapping. That is, for instance, for color, you would say at the color green, I'm just summing across all the activity that is along these lines here. Maybe I do this with some spatial filtering, a whole range of hue lines here. I'm just summing, and typically would be summing all supra threshold activation. And then that sum gives the input to this location. So for instance, if there's a peak here, the sum across the horizontal would induce an input to this hue field, and similarly across this location along the color axis, summing across space would give some input, while up here, for instance, there is no suprathreshold activation, so summing does not give any input to this field. So you would have these two peaks that represent green and blue. And very analogously, you could sum along the color dimension to sum, put suprathreshold activity summed into this field of a space and across the board, and then it's only these two spatial locations where there would be some inputs to the spatial field, and it would therefore induce these two peaks. So these kinds of mappings are called contraction mappings because they reduce the dimensionality of the underlying joint representation. So this is the example we just looked at, where there are two dimensions and we're summing along one, and therefore we end up with a field over only one of the two shared dimensions. If these were probability distributions, we would call that marginalization. So when you're looking at a probability distribution of multiple dimensions, multiple variables, and you are just summing over those variables you're not interested in, then you get a probability distribution only about the remaining dimensions. That will be dimension reducing projection. And contraction mappings like this exist for other kind of dimensionality. So for instance, if you have a 3D field where in the third direction you have another variable, this would be actually a 3D field more typically, where the space would be actually X and Y, and the vertical would be color. And if you're now trying to extract a spatial map from that, you would sum along the color dimension and therefore overlay all the different peaks in different colors, and then extract from that a two-dimensional representation. And you could do the same. You could also sum across, take only the spatial representation within a particular color layer, summing over all the colors. No, sorry. Which direction did I just go? I don't remember, but I think you get the idea. Okay, so that's how you would extract the component dimensions. You can also do the reverse. That is, if you know the component dimensions, like this. Now we're getting to the pink elephant kind of idea, right? So you know there is something blue, and it's at this location, but you don't have any direct visual input. So this would be something that you would want to do if you do a mental map. You're trying to imagine or image a object of a particular kind. Now you could represent these component information, piece of information, by having a peak in the color field that's blue. That could come, for instance, from a word which you have represented by a node, and that node activates in the feature field a peak like this. And then maybe you have to have some source of spatial information, maybe from past experience. And in each case, you don't know the other dimension, right? You don't know where the blue thing is, or here you don't know what color is at that location. So the mapping is an expansion mapping where every location in the field that is consistent with the dimension, with the value along the one of these two dimensions, here the color dimension, gets the same input. It's a rich input, right? And similarly along space, along color. Every location for any color gets a boost input. Now, you can see that with DFT, we could arrange that this leads to a peak only at those locations where these two ridges overlap. Now, there will be twice as much input there, or the two inputs sum at that location, and you could arrange for the detection instability to occur at those, when these two ridges overlap, and then a peak is induced. Now, this will be sort of boost-driven peak, right? The two inputs are larger there, and then they create a whole peak. And therefore, you have now created an item in your field that represents that particular combination of features, even though you didn't have the original input in the original space where the features are already bound. So that's why how you would represent a blue object at that location. So these expansion couplings generalize. You can imagine that, this the example I just showed you. You can imagine that you can do this in 3 dimension by, for instance, having a slice input, as I call it. So where along, let's say if this was X and Y would be space and the third would be color. If I know the color, I activate all spatial locations in 2D that match that color, and that would be very analogous to the ridge we're just looking at. Or also it could work in the other direction. That is, you know the location of an object, you don't know its color, and you would expand the 2D location into a 3D activation, would be a column input, right? The whole column along the different colors here would be activated by that input. It's a generalization for ridge in 3D. Yes?
I'm still stuck with the Strobe phenomenon a little bit. I was wondering if we had a projection from the color field to, say, the word representation of color, would the inhibition associated with color activation result in similar phenomena in the projected field, in the field which we're projecting?
Yeah, so you're referring back to Strobe, right?
Yes.
Yeah. So there is a new element there that does not show up here so far, which is competition, right? So it will be a need to either select the color that comes from a feature field or select the word, the response from the word, the meaning of the word, right? And this does, for instance, you would be responding by saying the color, saying a word, and that word would be competing with reading another word. And so that competition, that will be a selection decision in the space of words. And it's that competition that is the cause for the phenomenon, because there would be the notion that the word you're reporting is an activation from a color representation. So it could be, for instance, really a color representation, like this here. Let's say somewhere you have this peak because you are attending, maybe you extracted, let's go here, you see there's blue here, right? And that was part of a ladder of a word written in blue. And you are able to extract the color, and that color would activate a concept node, a word node for blue. And that's what you're supposed to report. And at the same time, there would be another level of representation where whole words are read, and I haven't asked the question of how that's represented, and they feed directly into a concept like the word read, and that word is now competing with a word that is activated like that, and that is the cause of the Strobe effect. So one could say there is an element of the Strobe kind of phenomenon that this describes here. It's the element, it's a part of grounding that you're able, it's actually the direction of grounding called description. When you see something, can you activate a word? You see a scene and you can say, oh, there's a cup and the cup is blue, and you could do a description like that, right? You can do that all the time. Here you get a task. The task is to describe the color in which letters are written, and you can do that from the scene. That's generating a conceptual response, concept meaning discrete, categorical things, from a visual array. And that part is overlapping with that. The competition is this automatic activation that when you read, when you see the shape of a word, it automatically activates the same concept that is just designated by the writing itself. You see, if you think of Chinese letters, maybe it will be most obvious because it's the sign itself, right? And that sign activates something. And if you're now asked to report the color of, it's the sign for red, let's say, right? And so that's really a shape or a pattern recognition. And if you're now asked to report the line, the color of the lines with which the Chinese sign is written, you would have interference if you know Chinese. So if someone who knows Chinese would have a hard time saying black when the sign means red. And the black might be, I don't know, it's not a good example. It's green and red, right? The sign is written in with green lines, and the sign means red, and a Chinese speaker would then have a certain probability of making a mistake. So that shows how special it is, right? It's kind of amazing that just having learned to read and write creates this automatic activation of the concepts. I mean, you can see that when you drive around. For instance, I was actually in Japan on an occasion, and they sometimes write, and I don't speak Japanese and don't read Chinese signs, and you have all these advertisements, and they mean nothing to you. And then they sometimes use English words, actually often made up words that are not real English words in advertisement. But they have Latin letters, and the words make phonemic sense. They are pseudo words sometimes. And they pop up. I mean, they're automatically activated, right? So that's more what that is about. And so it does overlap a little bit. So a theory of that would ultimately have to deal with things like that. But it's sort of not directly connected to the binding. I mean, there's some binding in there, but it's the Stroop phenomenon is not directly a measure of binding.
I was mostly wondering how inhibition of the surrounding field would affect phenomena bound to the surrounding field. Like we see inhibition around the effect, right?
Yeah, so I mean there are selection. I mean the task is a selection task, where you have to select one response. Let's say the responses are color words, and you have to maybe type them or press some buttons with these color concepts, and could be some questions of how these buttons are learned. If they have if it says the word on the button, or if it says, if there's some color on the button. And so we know that selection requires inhibition because you're pressing other options, and all these effects, like I reviewed last week, pretty much all these reaction time effects have to do with that the different alternatives that are possible in a task and get some activation in the task from the task set, from having a pre-activation pattern based on the instruction of the task, that they ultimately compete. And if you bring more competition into that, it takes longer to select the right one. And so that's in the problem with the Stroop task is that is not a task that lies directly in one of the feature spaces we have modeled so far. So far, we've modeled slow dimensional feature spaces that are not really categorical in nature. Well, if you're responding different words, these are categories, and how do you select among categories is actually is a topic, because you have probably in your mind people think like a couple 100,000 concepts. So it's a large number, but not infinite. So it's a real limitation how many different concepts you have in your mind. And so is there competition among all of those concepts? No, it's probably not. It's only some by the task. You can sort of pre-activate only those that are now competing, while the others are way below. And so let's say if your task is to say color words, then all the color words presumed by the task will be competing. That forms, it's not quite a field, but it is sort of a subspace at least. And then the competition in that domain would be mild if, I mean, it's competition, but it would be effective if you are just describing the scene. So you're just seeing this and have to say green, and that the way that these categories, and I haven't explained that so far, how categories are emerge from DFT, it will be an expansion mapping, right? That you would get from from a peak like that, you would activate a signal node. I think I have that. Maybe next week I even have an example for that. And so what would happen is that within that field of means it's a field with discrete entries, but they all compete with each other. So it's a field in that sense. There would be more competition if another location in the field also gets input, and that input is unexplained yet. That would be the input from the word reading system that also activates automatically without you being able to really suppress it activates color concepts as soon as you see the word.
Okay, thank you.
And we can come back to this if you're really interested in this group, because I will be talking about concepts in a little while, in like 2 lectures. In January, I will actually definitely talk about concepts. Good. So I was here, right? Mental maps binding individual features into bound joint representation. So this is, you see, already here we're getting to something that is no longer purely sensory motor. I mean, still, these feature space fields are still stuff we have in the sensory motor domain. So if we get this input here, we can generate these peaks. But when we do this, we're already doing something really mental, right? I feel like I ask you to imagine something. So that's how that's going to be important. I just mentioned that other pattern couplings will be coming up. So I'm talking about coupling from field to field. And the question is, are they dimension preserving? This would be one-to-one, contracting or expanding. And this is actually a form of expansion that just shows that what we're just getting at this would be a concept node. So this node here would activate, for instance, particular spatial regions. This would be for a concept like to be to the left of or below, something like that. You could see this along this dimensions, maybe only certain regions in the space that are to the left of this point would be activated. We'll get to things like that. So this is where the binding problem arises, and the binding problem is a famous problem that's been discovered forever, discussed forever in cognitive psychology, which has to do with these illusory conjunctions that misbindings can occur. So, for instance, if you had the task to make a mental map of a blue item and a green item at this location and at that location, if you use the same trick, you get 4 possible intersections of these ridges, because you don't know, is the blue item the left one or the right one, right? And similar for the green one. So if there was actually an underlying scene where the blue item is in fact here on the right and the green item is here on the left, you could do misbinding. That is, you would have an illusory conjunction where you think the green item is at this location or the blue item is at that location. So this does not happen a lot, even though I hinted that it does occasionally happen. And that is one of the pieces of evidence for what is called an attentional bottleneck, namely that when you're doing a task like that, you're doing it one object at a time. And that's important. It's one object at a time, which really translates here into one location at a time. You're tending to, so one location was this, right? When you have one location at a time, then you don't have a binding problem, because now you know exactly. So even have multiple feature fields, like different colors and orientations, so on, but they're all at the same location. You could still create an item that has the correct dimension, and I'll have to get to that in a little while. Good. And so the last point about this very simple example is when you now combine expansion and contraction, and that leads to what is called the cued selection operation. And that is sort of one of the most fundamental mental operators, if you wish, for higher cognition. So, for instance, underlies visual search. So here is the notion that this joint representation is maybe driven by visual input, or it could be created by a map. Doesn't matter how it comes about. You have these two objects in the representation, and now you want to say, where is the blue item, for instance? And this query, in a database, this would be a query, right? Or would be a search operation in your database. Search for the green item. Imagine you have many more items, many more dimensions. Now you would say, let's see all the green entries or all the blue entries. And the notion would be that that query would be represented in one of those low dimensional fields. So here, blue, that's your query you're looking for. And they do an expansion mapping into this joint representation. And then you can arrange that only those locations where this expansion mapping, this ridge overlaps with the two-dimensional input, a peak is formed. Or you could actually make the competition in the contraction mapping. You could maybe allow all of these peaks to exist, but there is more activity here than there due to this boost. And then in the spatial fields, you're going to make the decision. And that's ambiguous. Both might be the case under some circumstances. So that you can then make a selection decision about which spatial location is the one that was queued. And that's queue selection. And visual search would be, finding Waldo. Some of you know that example. Now that would be about knowing certain aspects of Waldo, certain feature values, but you don't know where it is, and therefore you would have to go through the scene and boost all objects that have the feature value expected, and then among those you might have to make a selection decision. Good. Now, the last 2 points, I'm doing well on time. I might be able to go to binding through space as well. So to go to more abstract levels of binding that are still analogous to this, I'll talk about role filler binding. And so here we're really talking about cognitive stuff, and I haven't yet explained really how to represent concepts. I'll make a first hint at that. So, for instance, when you say something like the green object, here we're using again the colors because we have ideas about the feature values. So something that's green, the green thing, or the green object, to the right of the red object. So you're using a color feature of an object in two different roles, right? Here, and this is the target of that sentence, that what you're trying the listener to pay attention to, or in your own mind that you're trying to select. While this is called a reference object. That is something that the relationship of being to the right of is anchored in. So it's to the right of that particular object, the red object. So this is an example of using concepts. I mean, if I call this a concept, the green thing and the red thing are concept, and I'm using it in different roles because could just as well switch the colors, but the role is dictated by the grammar of the sentence, which says, that to the right of, fixes the role of whatever the concept is here. And that is a very general thing. We just talked about Mary loves John, or it was John loves Mary. You see there, again, there's a role difference, right? When John loves Mary, then he has this grammatical role of being the lover, and she has the grammatical role of being the beloved. And it could be maybe generalized. He would be the agency, would be the patient, sometimes called the one that suffers something, that receives something. And he will be the acting, if the love is an action, acting. And sort of action phrases are like that, right? Here you have an agent that acts, and it acts on a target, for instance, like I paint a wall, and so I being the agent, and the wall is then the patient. Or I could have a tool. I paint a wall with a brush, and so brush is now used in a particular role. But in other instances, I could say, I grasp the brush, and now the brush is a target. While if I do something with the brush is a tool, and so on. And so there are many subtleties hidden in here, but the obvious one I'm going to get to is analogous to this Mary loves John kind of story. That we need to represent the concept together with its role in a phrase. And so that's important, not just in the mind, because it's also important really to ground that phrase. And ground really means, we call it perceptual grounding, means establishing a relationship between this mental representation, sometimes called conceptual structure, that the sentence represents, and something in the world, something we experience, or some action we do. So, for instance, if I have an image like this, then this green is to the right of this red. So, if you get that sentence, you would be able to say, the speaker is talking about this object here. That's the one that matches this description. And to do that, you would have to have some way of using your visual machinery where there would be a separate activation for objects that play the role of reference. For instance, this red object would be in a reference field, while this green object would perhaps be in a target field. That's along this dimension. This actually is here, this location, the target field. This will be the red one. And then you still have to deal with the relation I'm hinting, and we'll come back to that later, how that actually works. So this role-filler binding is a famous concept for how to do that. There are different proposals in the literature, including the Smolensky one I was referring to earlier that the VSA people use. And so for now, I will use a very simplified picture and will elaborate that picture over the next couple of lectures. And so I'm doing two things, and this may be good now in response to your questions about the Stroop effect. For who was that? Who asked that question? I just don't see the names right here. So the notion of concepts, simply speaking, you could say it's like a zero-dimensional field. So instead of a concept of red, it might be a population of neurons that stand for that discrete categorical concept. And you may know color concepts are discrete. Different languages have a different number, but small number of color concepts. Maybe some languages only have 3 minimally, some have 5, 10, 12, but it's not 50. And that might mean that there is, in this representation with hue space, there is a certain region in the space that a color concept stands for. So this population would have some connectivity forward, in the sense that, like a receptive field, that is, this node gets activation from a range of reds. That it is contiguous or not, that's a question of how I span the color space. But in the simplest case, it would be a local region of the hue space where red is activated. And it could be bidirectional. That is, as I'm learning this color concept in a Hebbian way, I would also be able to activate a certain range of hue values when I'm looking for red, right? And so this is a contraction or an expansion mapping depending on the direction in which I'm looking. And so these connections would be typically in all kind of models bidirectional. That is, I can use a color concept both to classify colors that I have in my visual array as red and so on into categories, but also to modulate, for instance, in acute selection, to say somebody tells me look for the red, and then I can activate regions in hue space that correspond to red and make a ridge input into my search field and then pick out the red stuff. So that's these color concepts. And again, I'm using color because it's so simple. You can imagine for more complex objects where maybe shape plays a role, and maybe there's even some kind of functional understanding that you attend to particular features to recognize objects of like some of these tools we just talked about. That might be more complex features that we haven't really discussed so far. So that's color concepts. Now, the notion would be that these color concepts can now be activated, for instance, by speech. We haven't really explained how, but presumably by reading or listening, we would be able to activate a concept. Now that the language here refers to my color concept. And then these color concepts would then have to be in different roles. And there you see that we have to somehow be able to say, are we talking about red as target or red as reference? And so the cheapest version, for which there might be sometimes be evidence, is that we do have multiple copies of these concepts. That we have a representation of red as target and another copy of red as reference. And any other color concept would also be available in these multiple versions. If that's the case, that is a joint representation of the roles and the concepts. So that's one proposal. That's a proposal that we're making use of in some cases. That's a proposal that is reasonable as long as the different roles that occur, these are not exactly syntactic grammatical roles, but they are more something like semantic roles, but that these roles would still be limited, that there's a small number of them, so that you can imagine that you have these whole the subject for every combination of these values, of these roles with every concept. In other words, every concept would be spanning a little space. It's discrete because these roles are also discretely categorically different, but it would still be a field-like thing because we're talking about ridges. For instance, if I know red, I would, from language input, I activate all nodes that are consistent with that concept red. And if I, from some grammatical syntax machine in my mind, I know that red was meant as a target, I would activate all targets, the target dimension of all the words, and where they intersect, I would then have activated the red as a target. Similarly, I would do green as a reference once. Actually, an example was the other way around, so I should have chosen green as the target. Yeah, so that's one proposal to do role filler bindings. There have been other proposals in the history. People, for instance, here in Bochum, my colleague from Malzburg developed the idea that these neurons could have a hidden dimension, that a neuron would be oscillating when it's activated, and that the phase at which it oscillates could relate in different ways to the phase of other objects. So for instance, if you have activated target, it's a neuron that oscillates, and activate red, it's a neuron that oscillates. And if they oscillate in phase, then you would say, it's the red is the target. And if they resonate in some other phase, then they are not related. That is still entertaining for some people. There's now, I think my colleague von der Matzfeld doesn't believe in it anymore. There are some arguments against that. But just to show that it's not unique, there are multiple ways to do that. And Smolensky had a complicated proposal that is actually ultimately somewhat like that. Yeah, so that's called role filler binding, where the item is filling the role, right? The target, the role is filled by the red item. And so it would be strictly analogous to joint representation and using ridges, right? That will be expansion mappings. One dimensional target expands across all the color concepts. You see that these discrete categories still can be field-like if they share certain dimensions. All these neurons have an entry for target, and then also all these categories neurons have different entries for role, and therefore now you could use expansion and contraction in this space.
If we have such a conceptual representation that is likely not as closely related to each other as the original field, or possibly not as closely associated with each other, would the mutual inhibition still work the same for selection?
Yeah, I mean, so it's of course just a model. In models like that, we could now say that a lot of nodes like that are all mutually inhibitory, and that's how we could make sure that only one concept can be activated at a time. There could be cases, in fact, for concepts, we could actually have complicated patterns of activation where we could have multiple items here in this joint representation being active, and so this. And there are interference effects there where you could make misbindings, where you suddenly flip the role of target and reference. This often happens with these phrases when we use just very low-level concepts like the color concepts, and people get confused. Was red the target, or was it the reference? So it is analogous, and it's analogous also with respect that the competition doesn't always work perfectly. So sometimes you might be able to activate an item that is actually competing. And that's not different from feature dimensions that are more close to sensory motor surfaces. So we're saying these discrete categories are more removed from the sensory surface, because the discrete category really means it has a certain invariance property. It doesn't matter exactly which shade of red, how bright it is, what shape it has, or how large it is, would all just go to one concept of saying red. So the proposal is that within this conceptual world, there are similar dynamical ideas. Now, this is much less elaborated, and as some of you might know, and I assume Sven asking all these questions knows this, that this world of concepts is debated, and it's a complicated world. And some people even argue that we should abolish the notion of concept. In German, concept Begriff, and the Begriff is too ambiguous as a notion. So there are two very well-established notions of concepts. One is called prototype theory, where you think of concepts being represented together with the most frequent instantiation of the concepts in visual, or whatever the concepts are about, in motor terms or some other terms. Versus the exemplar theory, where you're thinking of having seen a particular instance and recalling the concept in terms of a particular instance. And there's a third notion of concept, which is sometimes called theory-based concept, where you have some kind of propositional discourse, where you like a lexicon definition of that. And it's consensus that all three kinds of concepts seem to exist, and different roles and development show up in different places, and therefore it might be misleading to call them all concepts. And exemplar and prototype are actually probably a little tied to each other, that you can transition from prototype to exemplar if you have enough experience and things like that. So that's a complicated field. So we're using very simple, low-level ways of talking about it. And so what we're talking about is consistent with what is called a prototype theory of concepts. Good. So this is actually what I planned for this lecture.